Swayam Prabha. Digital India. Educated India.
And thanks to Professor Shivramakrishnan for having hosted me for last couple of weeks. And it was really fun to kind of conduct this Gyan course on nonlinear spectroscopy over the last 2 weeks. And thanks also to the students who were part of this course. Deeply appreciate their commitment to this. It was a pretty packed course of 2 weeks. A lot of things covered, but hope they had something to take away. And this session happens to be the grand finale of the course, sort of showing the real results of contemporary results, which are all can be linked back to the topics that we discussed during the course. Of course, I won't explicitly mention that. I leave the students to kind of connect the dots. All right, as introduced, I'm an assistant professor at Wake Forest University. And I'm going to talk about exciton-polariton condensation. I'm not per se specifically interested in the condensates or trying to kind of demonstrate condensation. I'm not a material scientist making new materials, nor I'm a photonics guy making new novel photonic structures. I'm a spectroscopist. So I'm using strongly coupled semiconductor microcavities as platforms to explore many body physics using advanced optical probes. So that's the context here. Condensation happens to be one motivation to explore this physics, but condensation itself is not the real goal in this context. So because I usually don't rush through my slides at the end, I really usually miss acknowledging the people who have worked with me in creating the results that I'm going to show you. So I want to first acknowledge them. This was done, most of the work that I'm going to show were done by two amazing graduate students, Catherine Cook and Evan Kumar. They were both joined me and I started at Wake Forest University. Excellent grad students to have. Some of the work has been done in collaboration with the group of Professor Carlos Silva, who was initially at Georgia Tech, then moved on to University of Montreal. Esteban Rojas Gadjans, Victoria Cueres Cordero, and Raymond Malatesta were all his graduate students. Esteban and Victoria are here. They are now completed their PhDs. They have moved on to be postdocs at Columbia University. A lot of collaboration also with the group of Giulio Cerullo in Politecnico di Milano, specifically Lorenzo Uboldi, who was a grad student who visited my lab and spent a semester with me. A lot of collaboration. The samples come from collaborators, specifically from the group of Juan Pablo Correa Baena from Georgia Tech. Martin Dominguez Gomez, who's here, is the guy who's making a lot of our samples. I also get samples from the group of Vinod Menon in CUNY, New York. Rishabh Kaurav and Ravindra were both providing us samples. A lot of this work is not possible without help and support of great theory friends, specifically Eric Bittner at University of Houston and Andrei Piryatinsky in Los Alamos National Labs. So I'm going to highlight all their work, hopefully. Of course, we cannot live without this, right? We need money, we need funding, so I greatly acknowledge that. All right, you may not know where Wake Forest is. You might be wondering, what is Wake Forest? Wake Forest is in North Carolina. North Carolina is here. It's in a small little town. It's not a small little town, it's a city called Winston-Salem. It's between Charlotte and Raleigh, if you know, they're the two big cities. It's a private university, about 5,000 to 6,000 undergraduates and about 2,000 graduate students, so relatively small scale, not too big. I work in Department of Physics here. I started out in 2022. I call our group Quantum and Ultrafast Optical Spectroscopy, but that looked too lengthy. So we called ourselves Quantum UFOs, not because we are interested in UFOs, but why not? To kind of, motivate local interest in unidentified flying objects. So this is a kind of a brief view of our lab. A lot of optics there on the table. We do both ultrafast and quantum optics. That's our focus. So our primary goal is to understand many body physics of excitons. I will define what excitons are. We are interested in these excitons, which are coulombically bound electron-hole pairs generated in semiconductors, sometimes even observed at room temperature. We are interested in many body physics, how these excitons interact with the bath, with the environment surrounding it. The environment can be composed of phonons. It can be some dynamic lattice fluctuation, dynamic disorder. It could be many body interactions between excitons, or it could be light matter coupling. We're kind of interested in the physics of that, and our primary tools are two kind. One, those are based on ultra-short optical pulses, sub 20 femtosecond pulses, because we are interested in very fast dynamics. We do both pump probe spectroscopy as well as coherent nonlinear spectroscopy, more colloquially called 2D spectroscopy. And recently we have started exploring the use of quantum entangled light as a material probe. This is kind of an emerging perspective. I'm not a quantum optics guy, but I caught myself into quantum optics a few years back and sort of started exploring this. We have different kind of interest, excitons in two-dimensional perovskites, quantum dots, strong light matter coupling polariton condensates, and as well as dedicated work on developing quantum photons as optical probes. I'm not going to talk all of them. I'm going to talk about a few of the recent work which are highlighted in red. A lot of work, but I'm going to show you a snapshot of everything. All right, semiconductors. So we all know semiconductors, and the characteristic of semiconductor is that you have electrons in the valence band, nothing in the conduction band. You come with light, you optically excite electrons from the valence band to conduction band, leaving behind the hole, right? These are positive and negative charges existing in a real lattice. They're going to bind themselves together, much like a hydrogen atom. Then I can move from this space defined by the crystal momentum to a space defined by a center of mass momentum, where you're accounting for these Coulomb interactions. And we can write out the eigenstates of the system, which happens to be excitons, which are much like the Rydberg states in a hydrogen atom. You have 1s, so on, all the way to the continuum of states, and the difference in energy between the lowest 1s state and the continuum giving the exciton binding energy, the energy essential to dissociate this electron hole pair. Typically, in most of the semiconductors, like three-dimensional semiconductors, the exciton binding energies of order of few MeV. So at room temperature, or even sometimes at low temperatures, it's very hard to observe excitonic features because the binding energies are extremely low. But in quantum confined systems, either two-dimensional quantum confinement or sometimes even 3D quantum confinement, you can increase, because of electronic as well as dielectric confinement effects, increase this binding energy. How do we know this exists? The characteristic of excitons can be observed in optical spectra. So if I take a semiconductor, you know, if I take an optical absorption spectrum, there will be no absorption till I hit the band gap, and then you have the free carrier absorption. In the presence of the excitons, you create additional resonances which are just below the continuum. You can kind of see all kind of Rydberg series if you're careful enough and if you're lucky enough. Okay, and then you can read out the binding energy by measuring the distance between the primary exciton and the continuum band. Like, this is the signature of excitons in optical spectra. You will also see some modification in the continuum band in the presence of Coulomb correlations, which is given by Sommerfeld factor. Going to go into too much of that. But you know, there has been some interest in excitons because in general they increase absorption cross section. They generate very sharp optical resonances, much like in atomic spectra. But also they can be used for some applications, especially light emitting, but also in some photovoltaic applications, although some energy is spent in the dissociation process. Our interest here is that they have the sharp resonances which can be coupled to light. That is our primary interest, especially because they have very large photoluminescence quantum yield, which means they have very large radiative decay rates. Okay, now what we do is that we take these excitonic materials, put it in between two mirrors, what we call as a microcavity. Okay, in the microcavity, you kind of excite your excitons. Excitons will decay, let's say, generating a photon, and the photon is kind of trapped in your microcavity, and then you can be reabsorbed. There can be cycling of this exciton and photon within the cavity, eventually hybridizing them. Okay, you can hybridize the exciton and the photon, creating what we call as polaritons. Polaritons are hybrid light matter quasi-particles in certain strong coupling limit. And in that case, if I take, for example, the momentum space representation of my exciton and photon. In this case, this is my momentum, this is my energy. This is the dispersion of a photon in a microcavity. It's parabolic. And exciton for this momentum range is relatively flat. When I couple these two, I create my upper and lower polariton branches, this kind. Now, how do we know this exists? You can do a simple angle resolved reflectivity measurement. So you can take your sample material, put it between two mirrors. Well, easier said than done. There are strict conditions. This has to be a microcavity with the distance between them of the order of the wavelength of light, so on and so forth, carefully engineered cavity, and do a reflectivity measurement. So come with white light, reflect, and the reflection of the energy of the photon will have very strong dependence on the angle. And you can kind of map out the dispersion of the upper and lower polariton branches. Okay, and that is a characteristic of presence of strong coupling on polariton. And over the years, there has been several materials which has been used to kind of explore this process. You have in the beginning inorganic heterostructures, gallium arsenide, aluminum gallium arsenide heterostructures, organic molecules, organic semiconductors, as well as inorganic hybrid materials. I have not put TMDCs in this two-dimensional materials. They're also excellent candidates. I've not put it because I don't work on them. We work on other things, so I didn't include it. So many materials have been explored. And one of the primarily kind of motivation to explore this is because polaritons are bosons, and in principle, they can form a condensate. They could all collect under the right condition. They could all collect at k equal to 0. It macroscopic coherent state, sort of akin to a Bose-Einstein condensate. It's not technically a Bose-Einstein condensate because it's under non-equilibrium conditions. It's not really in the ground state. It's an excited state, but still the lowest energy state of the excited state dispersion. Okay, and this macroscopic coherent state can emit coherent light. And unlike photonic laser, which has a threshold, this does not have a threshold because you just need to populate some density of polaritons. There's no population process. You generate macroscopic coherence. Okay. The problem in this simple picture is that in this picture, we only consider the presence of what we call as polaritons. Yeah. The cavity mode that generates, it has to be resonant with the exciton. So in this case, we'll be about 2 electron volts. Yeah, because these are exciton-polaritons. You can make vibrational polaritons in the vibrational frequency, so on and so forth. It depends on what is the discrete material state that you're considering, which are coupled to the photon. All right, so usually take your exciton, photon, couple it, you form 2 polaritons. The reality of the matter is that if I consider, let's say, n molecules, n number of molecules I put in the cavity, one molecule couples with one photon to generate your 2 polaritons, you still have -1 molecules which are not coupled to the photon. This is what we call as a dark reservoir of excitons, which are still eigenstates of your system. This can be solved in what is known as a Tavis-Cummings kind of Hamiltonian. And what you really have is that in addition to upper polariton, lower polariton, you have this gigantic reservoir of dark exciton states which are ubiquitously present. In this kind of condition, the efficacy of the formation of the condensate depends on 2 important scattering processes. It depends on the scattering of population from the reservoir into the lower polariton, as well as polariton-polariton scattering driving the population to lowest k equal to 0 state. And as a spectroscopist, I want to be measuring interaction parameters, and I am interested in measuring the interaction between this exciton reservoir and the polariton polaritons. When I say interaction parameters, they manifest either in form of energetics or the time scales. Right? This is a thing that I'm interested in. So as I said, this is an example, an early example taken from a review from Yamamoto's group of what happens when you form a condensate. You photoexcite the system. This is emission from your polariton, nice lower polariton dispersion. As you pump slightly harder, and you'll start seeing very nice emission all happening from k equal to 0 with very, very well-defined coherence. And in fact, there's a kind of comparison between polariton lasing and conventional photon lasing. And you can see that the lasing threshold for polariton laser, it can be orders of magnitude lower than photonic laser, which can make more effective and efficient photonic lasers. And that's why there is an interest in it. Okay, so now let's go back, take a step back, try to build a very simple fit. So usually we do a non-resonant pump simply because it's more convenient. Eventually, when you want to make a technology, you want electrically injected things, which you want to inject somewhere in the conduction band, hope the excitons will form. But you can also do resonant pumping. The challenge in resonant pumping is that because the cavity is made such that the cavity is mode is trapped, it's very difficult to go resonant inside the cavity and pump it because of the design of the cavity. But in principle, yeah, you can pump resonantly. But even if you pump resonantly at k equal to 0, there are processes which scatter the population into the reservoir at very fast time scales. In fact, I will show you some examples of that, which will intrinsically limit the condensation process. Okay, let's go a step back and build a very simple phenomenological model of condensation, where there is no real mechanistics inside here. It's just phenomenological. So I'm looking at the population of polariton at k equal to 0. This is a kinetic equation, rate equation model. There is some decay rate defined by the polariton lifetime, which is mostly limited by the photon lifetime in a microcavity. You have some nonlinear interaction parameters, which also unradiatively quench your population at k equal to 0, either through interaction of the population with the reservoir, with the polariton, or polariton-polariton. And the interesting thing is this: you have a term which ensures transfer of population from your reservoir into the lower polariton state. And the most important phenomenological term is this bosonic enhancement factor, where beyond certain threshold, this will become a nonlinear process. It will start populating, and that's why you see an exponential increase in the population at k equal to 0, and thus emission of the condensate. Now, the critical process is how do we ensure population reaches the k equal to 0 point. That is the most important thing. You have the lower polariton. You want to be able to dump enough population beyond this critical threshold. I'm not going to the mechanistics of what that threshold would be, but simple thing is we have a threshold density. It needs to go beyond that. It's kind of related to a de Broglie wavelength of the polariton. Let's not go into that for now. I want to be able to effectively dump the population at k equal to 0. There are several mechanisms proposed. Okay, one is called radiative pumping. The idea here is that if I detune my cavity such that my lower polariton matches exactly with the photoluminescence of my exciton reservoir, then I will radiatively transfer the population from the reservoir, absorption of the reservoir here, there is a Stokes shift emitted directly into my lower polariton, this radiative pumping. But you could also have other processes. For example, if I have population at non-k equal to 0, I could have polariton-polariton scattering, driving the population down, or I could have some kind of phonon emission process, vibronically assisted relaxation, dumping the population to k equal to 0. And depending on different configurations, material systems, each of these has been explored. One critical aspect is that we still don't know. If you ask me, what is the magical recipe that will ensure I'll form a condensate? What is the material that you want to produce? I have no answer. The reason is it's so complex, or we don't completely understand it. The primary reason is also that we are not able to unambiguously quantify these interaction parameters to be able to say, hey, this, and this are the material determinants of the polariton condensation process. And that's a challenge. So dark excitons do not form a condensate. They are just a reservoir of the population. The condensation happens only from the lower polariton. So the reservoir exists. You have to live with it. You cannot not have it, unless you decide to make a strongly coupled microcavity with one molecule, which is possible, but it's not really technologically relevant, I would say. The reservoir density can be orders of magnitude higher. That is, orders of magnitude higher. Right. So here I'm going to quickly go into our story. I'm going to show three different examples, three different spectroscopic studies. One study done on a system which forms a condensate, where we want to again identify these interaction parameters. Remember, I want to show that. So one which forms a condensate, one which does not form a condensate. Two very different systems, but we will talk about that. And thirdly, and based on these two, I will highlight the need for newer, novel techniques in order to extract one important parameter called polariton-polariton scattering. And motivated by that, I kind of, not going to demonstrate, but kind of propose a methodology here with which we think we can access polariton-polariton scattering parameter. All right, story one. I'm resolving the formation and decay dynamics of an exciton-polariton condensate. So we have taken a system, a simple molecule. This comes from the group of Vinod Menon, a close collaborator. He has shown in 2024 that if you take a normal rhodamine dye, everybody knows rhodamine, you kind of enclose it in some kind of chemical host. It's called SMILES. Don't ask me the acronym. It's chemistry. I don't know chemistry. But let's say I'm able to make this host such that I reduce intramolecular interactions. That's a very important thing. No interaction between molecules driving quenching of the population. In that scenario, when I make this complex and put it in a cavity, I do see a very nice condensate, which can be seen both in the momentum space representation of the emission, where you see emission happening only at k equal to 0. You also see very strong, very narrow peak emerging beyond certain threshold density, which are both signatures of a condensate. All right, so now we want to measure the dynamics of this condensate. Easier said than done. We can try to do time-resolved photoluminescence, but time-resolved photoluminescence, you don't have a method based on, say, TCS-PC, time-correlated single-photon counting, and even streak camera-based methods for molecular polariton condensates, because everything happens within a picosecond, and your time resolution is picosecond. So you want to have something which has high resolution. To do that, kind of use a technique what we call as ECPL, excitation correlation luminescence spectroscopy. The idea is very simple. You come with your laser pulse, split it in two, you modulate the pulse at two different frequencies, you combine them back, put it into your sample, collect your emission, and integrate that emission in a photodiode. Okay? So now, if I look at the integrated intensity of the photodiode, I have photoluminescence coming because, or emission coming because of my first pulse, because of my second pulse, and the third term coming because of interaction between the pulses. Okay? Now, if I want to extract only the nonlinear part, what do? I demodulate the signal at the sum frequency. Okay? When I demodulate the signal at some frequency using a lock-in amplifier, and I measure what is called excitation correlation photoluminescence, which is pulling out the nonlinear part. Now, why is this important? In the case where my steady-state PL is scaling linearly with density, then there is no nonlinearity in the system. My ECPL will be 0. But in the case when my steady-state photoluminescence goes superlinear, like for example in this case, then you will start measuring positive ECPL signal. Presence of both pulses gives rise to an additional photoluminescence signal, which would not be present if one of them was missing, right? So you'll get the total photoluminescence, which is greater than 2 times photoluminescence from each of the pulse. Then why is this important? Remember, when I have the condensate, you have the nonlinear increase in the photoluminescence intensity, because the condensate has this bosonic enhancement which pulls the population, and there is substantial enhancement like in a laser in the photoluminescence. So it's intrinsically a nonlinear process. So if I keep both the pulses below the threshold, okay, then I will be able to observe, if I'm able to observe a nonlinear positive ECPL signal, that would be a signature of the polariton dynamics. And here, the time resolution is simply limited by the line width, the temporal width of a pulse, which we can make it as short as we can. These are the dynamics that we have shown. I'm not going to go into too much detail, and you can see not much ECPL signal below the threshold. Above the threshold, it goes really nonlinear wise. This was all done by Evan. If you're interested, there's more in this archived paper, just under review right now. And we are able to time resolve the formation and decay of the condensate. Remember, there's a formation time, which is kind of fascinating. A formation time of about hundreds of femtosecond, about 300 femtosecond, and the decay lifetime, which lasts few picoseconds. Now, spectacularly, something is happening here. when I calculate the polariton lifetime, the lifetime of my photon in the cavity, it's about 95 femtoseconds. It's 95 femtoseconds. Okay, so the photon lives for extremely small period of time, but we are seeing the condensate form and decay in a time scale much longer than the photon lifetime. Obviously, it has a source which is feeding the condensate continuously. What could that source be? Our reservoir. And we are basically looking at the dynamics of this feeding and defeeding process, if I may call it, through our nonlinear dynamics. Now, we can build a model here, a simple model through a radiative pumping process. You create a population, it transfers with a certain rate, which is competing with the decay rate limited by the polariton lifetime. We could get reasonably good fits. I hope you agree it's a reasonably good fit. It's not spectacular, but it's not bad. But the story is, this fitting is fake. This fitting is fake because, remember, there are these terms of radiative transfer rate and polariton lifetime which should not change with my excitation density. They are intrinsic properties of my material polariton system. To be able to fit this data, I had to change it. Otherwise, it wouldn't fit. You can kind of see it already in the process that the formation time slows down as I increase my excitation density. Formation time slows down. Now, any spectroscopist in the room will know if I increase my excitation densities, dynamics will become faster. They will never slow down. Here, things are slowing down. The reason it's slowing down is because at high enough densities, we are opening up additional, below zero time. Oh, this is because we are using two identical pulses. So they are kind of symmetric on both sides. So if you do a measurement on this, it's similar to this because there are two identical pulses. There is no time ordering in that sense. All right. There is an additional channel, additional population, which is feeding in the condensate in addition to the reservoir. Okay. Do we have a proof of that? We don't have a direct proof of that. We did careful density dependence below the condensate. And what we have seen that as we increase, we start seeing population, non-trivial population at higher lying K states. There's higher lying K states, which is populated more and more for whatever reason at high enough fluences. So at high densities, you have this population not only in the reservoir, but higher lying K states, which is adding additional channel for the population to relax into the condensate. Okay, so that's a source of polariton in addition to radiative pumping can be observed, particularly at high excitation densities, which populates the condensate. The hypothesis, the working hypothesis is that these are higher lying K states. I have not demonstrated it, but it's an ongoing process, but I have kind of alluded to that fact. Okay. Yes, it is decay superradiance at the end of the day. I have not used decay model simply because of the complexity of the model. The kinetic equation works. Yeah. I'm a bit skeptical of using decay also because it works in the Coulomb gauge. Is the Coulomb relevant gauge for condensate, especially with photons? I don't know. So there are some issues there. Yeah, it is. Yeah. I'm kind of doing decay, I agree. Although I have not explicitly used Stavix-Cummings. I kind of did a phenomenological model. All right, so let's kind of go into the part two. So in the first case, we have polariton lifetime can be estimated simply by looking at the line width of your polariton in reflectivity spectrum that is related to the inverse of the lifetime. You can also do a transfer matrix modeling calculation. Okay. All right. So when I have the condensation, I know there is source of my reservoir and higher lying K states. Both are aiding the formation of the condensate, right? I'm not completely exposed to all the interaction parameters, but I'm kind of tracking down the lifetimes here. Now let's talk about another case study of 2D metal halides, where I'm going to demonstrate many body interactions can impede the formation of the condensate. Yeah, in terms of the dispersion, how high can you go? again, it's not something we see about 20 to 25 degree emission. That's what we can quantify. Whether it's related to some material factors, I mean, it's composed of both material and photonic factors, which work in hand to determine how high the population can go to. Also depends on the Hopfield coefficients, how excitonic, photonic system are, because you're observing the emission. It depends on the Hopfield coefficients. That's right. That's right. It was his PhD thesis, I think. All right, so we're talking about this two-dimensional perovskite. It's rudolph copper lead iodide. So these are layers of lead iodide separated by organic cation. Organic cation is not participating in optical excitation. It's only kind of stabilizing the structure. So what you have here is electronic and electric confinement in the lead iodide structures, and lo and behold, in optical absorption, you get very, very sharp, well-defined excitonic signatures, even at room temperature. If I cool down the sample, I clearly see my exciton well separated from the continuum. You can get the binding energies to be about 200 to 250 millielectron volt, pretty large binding energies. Now, there is a side story here that if I cool down the sample, my exciton, at the exciton energy, I don't see simply one transition, but I see, I hope you agree that I see at least 2, if not 4 transitions, separated by about 35 to 40 MeV. Now, one important thing that you might think, okay, this is some kind of vibrational replica. There is no phonon at this energy in this material. So this is not a vibrational replica. These are distinct excitonic states. Now, we try to do cavities with this, done by Victoria and Esteban here. Very nice angle resolved emission. Now, a negative result is something that we cannot justify. We never saw condensate here, even at 5 Kelvin. These are all done at 5 Kelvin, by the way, and we have never seen a condensate here. And we were banging our head, okay, why are we not seeing a condensate? How can we make this material to see a condensate? Remember, the binding energy and photoluminescence radiative rate are extremely high, much higher, probably comparable to organic material systems. So this should be a fertile ground to explore condensation, but it doesn't form, at least to with our system. This is a slightly, so we did EC measurements again. We don't see any kind of nonlinear behavior, or we see nonlinear behavior, not positive nonlinearity, but we see negative nonlinearity over hundreds of picoseconds. What we are observing is all what's happening in the reservoir. There is strong exciton annihilation going on, which is dumping and killing the population. It is transferred to polariton, but nonlinear dynamics are dominated by exciton annihilation within a dark reservoir. But what we see is that whatever happens in the reservoir, we immediately see it in the cavity, which means that there is transfer from the exciton to lower polariton happening within the time resolution of our experiment, which happens to be about 200 femtoseconds. So we are seeing some transfer happening in 100 to 200 femtoseconds, and we need to resolve that. So we want to resolve the transfer of population from the reservoir into the lower polariton state, and for that we do 2D spectroscopy. So 2D spectroscopy, the young students will know this because I hammered this for several hours on this. So what we do here, we come with 3 ultra-short pulses, which are phase stabilized. You excite the material here. 3 field interactions generates third order polarization. Third order polarization emits radiation by phase matching condition along the 4th direction. I can measure the amplitude and phase of that emitted radiation by heterodyning with another local oscillator pulse, which is going in the same direction. Now I can, in a quick story short, I can now develop these 2-dimensional correlation maps of a linear absorption spectra, which look like this. You have some diagonal features and off-diagonal features, which represent something. Usually diagonal features represent population, presence of population, right? Off-diagonal features represent presence of coherences or interactions between states. The simple interaction or coherence could be mediated because they have a common ground state, but also can manifest because in the presence of coherent energy transfer, which is what I'm going to use right now. So this is one snapshot of 2-dimensional spectra taken on this our perovskite polariton semiconductor microcavity system. Ignore the negative sign, that's more a convention. Again, GAN students will know this is a refacing spectrum. And what you will see are some features on the diagonal, and this is the energy of the lower polariton, the higher lying polariton, and there is some feature on at the energy of the exciton reservoir. So all this corresponds to population of the polariton state. This is resonant because we are coming the short pulse with a broad enough bandwidth that we can excite lower polariton, some reservoir is populated inevitably, and some higher lying polariton state. What is interesting is that as we evolve this, going from 20 femtoseconds till about 140 femtoseconds, very short times. See, is firstly, this cross peak between the lower polariton and the reservoir kind of increases in intensity. It increases, the cross peak increases. And this is a signature of transfer of population from the reservoir into the lower polariton. Okay, transfer of population from the reservoir into the lower polariton. Okay, that is observation number 1. And that is happening within 150 femtoseconds. So very fast time scales and within the polariton lifetime. So effectively dumping the population in the lower polariton k equal to 0 state. However, I'm not seeing condensate. I'm not seeing condensate even though I'm dumping the population very fast. And if you look closely, if I zoom in on this diagonal feature and take a cut in this direction, you will see a blue shift in the peak here. There's a blue shift in the peak, which can also be seen in the full width half maxima contour maps of this feature here, zoomed in here. And what we can learn from this, a lot of detail here, what we can learn is that indeed the population relaxes from the reservoir into the lower polariton, very fast time scales within the cavity lifetime. However, it doesn't occupy only k equal to 0. You start having depletion and the population starts going to non-k equal to 0 states, which is somehow inhibiting. There is some strong repulsive interactions scattering the population out in that direction. Okay. So why is this the case? Why is the scattering so strong? And typically in a system well characterized, well detuned like this, your lower polariton at k equal to 0 should be strongly photonic. When I have strongly photonic character, your nonlinear interactions are by definition, photons do not interact, should be very, very strong. Polariton scattering should be weak, and these are carefully engineered to that purpose. However, what we see here is that there is depletion of this through a polariton scattering process. Why is this the case? Now, if I go back and look at my reflectivity spectrum, this is angle resolved reflectivity. As I remember, there are multiple excitonic states. In fact, when you see the polariton dispersion, we see at least 4 polariton states, 4 polaritons. And if I plot out the Hopfield coefficients, which is relative fractions of exciton and photonic character of each of the polariton, at the lower polariton, because of presence of multiple excitons which are contributing to the coupling, what I see here is that my lower polariton k equal to 0 is intrinsically strongly excitonic. And this strong excitonic character of my lower polariton at k equal to 0 is driving polariton scattering, inhibiting the population of k equal to 0, thus inhibiting or impeding the formation of a condensate. Okay, so a side story here for a few minutes. Now I said this presence of multiple excitons is the one making the lower polariton strongly excitonic. And if I want to remove this, I want to kind of remove presence of this multiple excitonic states. I want to ensure there is only one excitonic state, right? If I have only one excitonic state, then probably I will reduce the excitonic character of my lower polariton, thus helping the formation of a condensate. Okay, but for that we need to, it's a very interesting question to ask, can I tune my material so that I can suppress my other excitonic states, so that I can have a singular peak? That is probably yes, and the answer probably lies in understanding why these excitonic states appear in the first place and what is their character. Now there are at least 3 excitonic peaks and 1 photon state, and this is a Jaynes-Cummings model, by the way. You couple them and you form 4 polaritons. Not exactly. So what is plotted here is the absorption spectrum of the 2D perovskite, and you clearly see the peaks very nicely. And these are well-defined peaks. There are no higher lying states. We are far away from higher lying states here. And these are kind of can be numerically mapped onto the polariton dispersion. 2D perovskites, the binding energy is so large that you can isolate the exciton extremely well, right? And so you can kind of see the nice polariton structure. These are not Rydberg states. These are distinct, some kind of splitting fine structure in my exciton. No, it's not exciton molecule. It's excitons. I'm going to show you they're exciton polarons. Basically, excitons occupying different lattice configurations. That's because of the softness of the lattice. Okay, let's quickly kind of go through this multiple exciton states. The question kind of motivated that. These excitons come because of the lattice interactions. The multiple excitons exist because there are multiple phonon modes, each driving different kind of lattice coupling of the exciton, what we call as exciton polarons. How do we see this? So we kind of think about not this way, where you simply draw two states here, but I'm going to represent this in a coordinate space where I can draw potential energy surfaces of my ground and excited states, XB states, as a function of phonon coordinates, and there is kind of lattice reorganization intrinsically present, sort of a displaced harmonic oscillator model in the presence of the excitonic states. How do we measure this? Measure this using a technique called resonant impulsive stimulated Raman scattering. Wrong story start. You just hit your system like you hit a tuning fork with a hammer. You hit a tuning fork with a hammer, you give impulsive force, you generate all the normal modes in the lattice, okay, and then you hear it, right? And then do Fourier transform. Well, your here cannot do Fourier transform, but let's say if we had a Fourier transform skills, then you'll get a vibrational spectrum. And that's what we do, pump probe spectrum. Because we have short pulses, we can give impulsive forces, generate these coherences and watch them in time, and then Fourier transform to get that. This is a spectrum, a pump probe spectrum. This is a pump probe spectroscopy. Here is the detection energy, the probe energy, pump probe delay time, some decay happening. If I remove the decay, I'll see beautiful oscillations here, and these are coherent phonons, basically impulsively generated. But there is a kind of a detail here which is exciting for us. If you look at this modulation, it has certain line shape. So there is modulation here, there's modulation here, there is no modulation right at the center. And this so happens to be the characteristic of this displaced harmonic oscillator model, right? In fact, I can take a Fourier transform. You can see the beating energy in the MEV. These are our phonon energies. So this is the phonon spectrum, a Raman spectrum obtained using a time domain measurement. So you would have heard about Raman spectrum in kind of using a spectrometer. This is obtained through a time domain process. And what you see here is that right where I have an absorption, I have a node in the modulation. I have a node in the modulation. And there is a kind of a line shape to it. And that is coming because of this displaced harmonic oscillator model. Lack of time, I'm going to skip this. We can model this using perturbative expansion and get an expression where we kind of relate the line shape to a very important critical parameter called Huang-Ries parameter, which is telling you how much of the displacement is happening in this case. And this is a measurement on made our system. We get a Huang-Ries parameter for exciton A and exciton B, very nice. But what is interesting now is that if you say all this optical absorption line shape is coming because each of these excitons have different kind of displacements, if I kind of engineer that Huang-Ries parameter, I could have a material chemistry handle to turn on and off these multiple resonances. At least that's our point. So we kind of explored this. We went and changed the organic cation. Sorry, so we changed the organic cation. We replaced this material chemistry. So we changed, this is phenethylamine that's sitting here. We kind of added a halogen at the end. And what we observe is that that Huang-Ries parameter has some form of dependency on the organic cation. Organic cation, which is not doing anything to electronic excitations, is only holding the structure, but it is changing my polaronic character of my exciton. Okay, I'm changing the polaronic character of the exciton. We kind of mapped it onto octahedral distortion during XRD, X-ray analysis. Not going to go to that, but the takeaway message is I could potentially use my organic cation as a way to turn on and off by multiple resonances. Can we do that? The answer is yes, we can do that. And it kind of shows up. You see PEA, multiple peaks, chlorinated even stronger, but fluorinated almost a singular peak. So we can tune this. Yeah, these are not phonon sign bands because the splitting energy is not a phonon energy. The phonons are all an MEV. That's a very good point. That's an open questions I don't have an answer to. Why you have multiple polaronic state coexisting? That's a problem I have no answer to. That's a very interesting theory problem. I hope somebody takes it up. Yeah. Okay, all right, so we can kind of engineer this. Due to lack of time, I'm going to skip this part. This is talking about biexcitons, not going to talk about that. So takeaway message is this. The transfer happens in 120, 150 femtosecond from the reservoir to polariton. There is evidence of multiparticle coupling between excitons and polaritons. However, repulsive polariton-polariton scattering prevents accumulation of the population at k equal to 0, thus impeding the formation of a condensate. Now, I've given two examples. In one example, I said polariton-polariton scattering is actually helping in formation of a condensate. In other case, I'm saying polariton-polariton scattering is impeding. The problem here is that I have not directly and unambiguously measured polariton-polariton scattering. The problem there is that most of the dynamics, because there's substantial population in the reservoir, the dynamics are dominated by what's happening in the reservoir. So that kind of makes me always see this convolution of the dynamics of what's happening in the reservoir and what's happening with polariton-polariton scattering. Now, if I want to remove reservoir completely so that I can directly observe polariton-polariton scattering, there's one way. Like we said, take one molecule, put it in a strong coupling regime. Kind of impossible to do it, although some people can do it, but let's say it's not something that we want to do. The other option is go with single photon and generate only one polariton, right, without anything in the background. Now, we all know if I go with such low fluences, short noise limit will not allow you to do any nonlinear measurement. It's impossible to do a measurement. So that kind of motivated us to explore other pathways to kind of see if we can extract this parameter using quantum light, specifically entangled photons. To tell you the perspective, the kind of picture that we developed, the perspective that we developed, experiments are ongoing, they're challenging, but they're ongoing. So the idea is this. I take spectrally entangled photons of this form. I'll come back to this form later. So basically you have, we have heard a great talk last week on spontaneous down conversion. I don't need to go back to that. So you come photo-excite or send a pump a nonlinear crystal, spontaneously you down convert the two photons. The two photons, what we call a signal idler, are correlated through what the energy of the signal idler are correlated through what we call the joint spectral amplitude function. I'll come back to that. And let's say I send these two photons through my material. Two photons goes in, there is some interaction mediated by the material, and one can expect that the joint spectral amplitude is modified through material interaction. Then after transmission, I do a quantum measurement, some kind of projection measurement to fully characterize my joint spectral amplitude, both in terms of its amplitude and phase. And the question that we are asking is that can that give us something about what's happening in the material? Okay, that's the kind of idea. There's some very nice theory papers done in collaboration with Eric Bittner's group, some two experimental papers which we have come out recently with, hopefully more coming soon. Okay, all right, so let's talk about SPDC in type 1 crystal. This is just type 1, let's not talk about type 2 crystal. So this is the wave function of the state. You have your two creation operators acting on your vacuum, and this is your spectral correlation between the energy or the frequency of the signal idler. Now what you will see, of course this is done in our lab through hyperspectral imaging. We can map out the wavelengths and the frequency correlations between signal and idler photons. SPDC happens via a cone. We can kind of generate broadband spectra. That's the idea here. We can generate broadband spectrally entangled photons in our. Now joint spectral amplitude, this is a simulation for both type 1 and type 2. It looks something like this. Basically, the way to think about it is if I detect a photon, let's say at 700 nanometer, the other photon has to be detected at 670 nanometers. If I detect a photon 670 nanometers, the other photon has to be in the complementary wavelength region, and you do what is called a coincidence measurement, which was already introduced in the week before. I was lucky to be present for the previous talk, so I don't need to reintroduce this. Okay, we can measure this joint spectral amplitude. The simple way is take the two photons, send them through your microcavity, separate them out, or whatever means you can, put it through spectrometers. Through spectrometers, so you scan your wavelength of each of the spectrometers independently, put two detectors, do a coincidence measurement. If you want to do this, good luck with that, because first of all, your photon flux is extremely low. Your photon flux is extremely low, and then your gratings are intrinsically lossy, and then on top of that, you're taking the first order diffraction of the grating and throwing away a bunch of photons. It will take roughly 4 days to get you a nice measurement done, which is not what we want. So we came up with a slightly different method. We replaced the spectrometers with inline birefringence based interferometers, Mach-Zehnder interferometers. This is motivated by or designed by the group of Giulio Cerullo, Politecnico di Milano, for something completely different, but we kind of explore that for this purpose. The idea is, instead of measure spectral domain measurements, we do a time domain interferometric measurement, measure an interferogram, do a Fourier transform, and get a spectrum. Okay, and in that case, what we are measuring is some kind of inverse Fourier transform of your joint spectral amplitude. Okay, at least that's the motive, that's the kind of formalism that we are working with. And this is an actual measurement done in our lab. That's done with a type 1 BBO, very nice joint spectral amplitude here. There is certain width here, it's not very narrow. That's because we are integrating all angles. We can clean it up with some kind of spatial filtering effect. I'm not going to talk about that, but we can do a measurement reliably of joint spectral amplitude. We can do it very well. Now let's ask our questions. Okay, you're doing all these efforts to measure this complicated function, but can it really give access to a many-body interaction parameter like polariton-polariton scattering? So we kind of said, okay, let's first kind of explore theory. And this is Eric Bittner and Andrei Piryatinsky kind of approach perspective. The idea is, okay, take this biphoton state, send it through your system. There is some second order scattering happening, transforming your input state. And in the most simple case, second order scattering is simply product of first order scattering, which is simply linear absorption. Two photons go in and then come out without any interaction. But let's say there is some potential mediating this interaction, then one could think that this joint spectral amplitude would be modified. Is this really true? We took a simple Hamiltonian, Hamiltonian with some interaction between excitons, and what we observed theoretically is that indeed, if this was my input state, in the presence of interactions, I see spectacular modifications in the joint spectral amplitude. So long story short, theory seems to predict that indeed, in the presence of interactions, I will see modifications of the joint spectral amplitude, which may be a way to quantify the interaction at single photon or biphoton excitation levels, which is kind of spectacular. So we started out with a simple linear response function. So we said, okay, instead of sending two photons through a strongly coupled microcavity, let's first benchmark our technique. So we took an empty photonic cavity, no material here. This is your dispersion. These are photonic modes. No strong coupling here, just parabolic photonic modes. These are input state. We send only one photon through the cavity. So what you would expect to see is filtering, spectral filtering, which means this joint spectral amplitude will narrow. Indeed, it does narrow. Which means our technique is kind of working. But it also does something very spectacularly interesting. It has this kind of anti-correlation or loss in the correlation that happens. I call this the ice hockey spectrum, which is an experimental observation, very reliable, very reproducible, but we have no explanation. So if I take simple input-output formalism, I can do this in Python with few lines code. The input-output formalism only predicts spectral narrowing or spectral filtering. It does not predict this kind of ice hockey stick-like spectrum, which is still an ongoing effect. We are still figuring out, which is still something kind of an emerging frontier for us, at least, to kind of see this intricacies. And the hope is At some point, we'll be able to send, some point soon, not too far away, we'll send 2 photons specifically at 2 specific K points in the polariton dispersion. Let the polaritons interact through polariton scattering and read out the joint spectral amplitude. And hoping that with that change that we can measure, we'll be able to estimate polariton scattering effectively. To kind of conclude, we have gone through 3 different stories now. One story where there is condensation, and I kind of alluded to the fact that there may be contributions from both radiative pumping, direct transfer from the reservoir to the condensate, as well as from polariton scattering. In another case, because of the strong excitonic character of the lower polariton, there is substantial polariton scattering impeding collection of the population at k equal to 0, and there may be some material handles to engineer this. And lastly, the common theme for the 2 stories is polariton scattering. We are trying to develop new tools based on entangled photons to read out the polariton scattering parameter. Okay, with that, I end. Thank you.